First of all, can everyone hear me at the back? Is that okay? If at any point you can't, please wave frantically, and I don't know how to fix it, but I'll at least know. So yeah, my name is Chris Pattison. I currently work at the University of Portsmouth. I don't often work on James Webb, but I am very passionate about talking about it because it's so interesting. So I will talk about James Webb and another new telescope called the Euclid Space Telescope, which I do work a lot on. I'll start with James Webb because I think it's the most visually striking telescope. And also, please do forgive me, I used to put my Twitter on here, but Twitter is an awful place now, and the only other social media I use is YouTube, so forgive me for putting that as the only way to contact me. But if you have questions beyond your one, you can come and find me afterwards, and I'm happy to talk. Right, before we start, I'm sure all of you are wondering, who is this person and why would I listen to them talk about space telescopes? So I want to do a very quick history of my academic career, I guess. So I'm actually a local person. I was born in Portsmouth, and I did my school in Waterlooville, if any of you know that. It's not too far. And then I thought I should travel a bit. I'll go up north to do my degree, so I went to Guildford to do my degree at the University of Surrey. And then you'll see I come much further south since then. So I actually did a maths degree rather than a physics degree. But towards the end, I realized all the modules I liked the most were the physics ones, so I made a switch during my PhD, which I moved back to Portsmouth to do in 2016. I spent about 4 years doing my PhD, and I was one of the first people to finish their PhD during a pandemic, which was a unique experience of spending 3.5 years working on something and then it finishing just in your spare room on your own, thinking, okay, that's finished, I guess. But luckily, I still managed to get a job back at Portsmouth, doing a few different things, mostly cosmology, which is largely a different word for astronomy, excuse me, but also a few other projects involving some medical research and now working on the Euclid Space Telescope. So this is an anomaly in the portfolio, but please ask me about it afterwards if you're interested in how I used astronomy to do medical research. It was during COVID and it was pretty cool, but I'm not going to talk about it in front of you tonight. And I just threw this up because I wanted everyone to know that my graduation photos are better than everyone else's because I took my cat. Right. So in order to talk about the newest space telescopes, I want to compare them to not the oldest, but one of the oldest space telescopes, the Hubble Space Telescope. So he will be one of our main characters tonight. Hubble launched in 1990, which was before I was born. And it has now been observing space for over 34 years, which is incredible and much longer than I think anyone expected when it launched. Most of these facts I will come back to in more detail later, but I just wanted to give you the fact sheet on Hubble before we start. It only cost about $2 billion before it launched, which nowadays is a pretty good bargain for a space telescope. I think the idea of it was first really put into motion in about the late 70s to have Hubble launch, and then 13 years nowadays is good. We have delays of 13 years on some of the space telescopes that we work on now, so this is great. And we expect it to last at least another 10 years if we just leave it on its own as is. It could well last beyond that, but it would need some intervention with some astronauts going to visit it, which they have done 5 times before. It's been serviced 5 times, so it's been upgraded and fixed on 5 separate occasions. The first one was very soon after it launched because, as we'll get to, it did not have a very happy first few years in space. And then I was just trying to find some other interesting things, so I found out it's about the size of a bus, which I think is remarkable. And 11,000 kilograms is very heavy nowadays for a telescope. All the more recent ones will be quite a lot lighter than that. And one of the main comparisons for space telescopes is the size of their primary mirror. So this is the main mirror that collects light, and for space telescopes, the bigger the better is easily the truth. And Hubble's is 2.4 meters. It doesn't sound too big, but building a mirror that is perfectly flat and reflective is really difficult to do at that scale. So this was very impressive, especially in the 90s. Although, they didn't nail it. And Hubble is mostly a visible light telescope, but it can see a little bit of infrared light and ultraviolet light. But again, I'll go into more details of all of that in a minute. So we can meet our second competitor, the James Webb Space Telescope. It looks quite a lot different, I think. Hubble is sort of a toilet roll tube with some bits on the side, and JWST looks very different. I will probably call it JWST, which is just James Webb Space Telescope. So apologies if I say that too fast. It launched in 2021 on Christmas Day. I made my entire family stop Christmas celebrations to watch the launch. Except, someone checked on the potatoes because they're important, but it was meant to launch, it was scheduled for like the 20th or the 21st, and then storms were in where it was launching, and it just ticked day by day later, and then on the 24th, we all knew this is happening on Christmas Day. We'll have to stop our plans to watch this. It cost a cool $10 billion to launch, which is quite a lot more than Hubble, but it also took a lot longer. So this was sort of first talked about in about the early 90s, just after Hubble launched. They were already talking about the next big telescope. So it took about 30 years to launch. The original planned launch date, the very first one was 2007, and then 2011, and then they admitted defeat, and 2021 was the eventual launch date. This is purely an infrared telescope, so it can't see any visible light. It's really making sort of heat maps of the universe rather than images that we would see with our own eyes. And as I said, bigger is better for mirrors, and JWST's is a gold mirror, and it's 6.5 meters, which is the amazing thing about it, and also what made this telescope so difficult to build and get into space. We're expecting it, when it launched, 5 years was the stated goal, but the launch went so well that it saved quite a lot of fuel on board, so we're now expecting it to last at least 10 years, hopefully more, which does sound very, very short when compared to Hubble's 34 years. But it did, comparison, it's much bigger. The mirrors, the heavy bits are much bigger, but because they're 30 years newer, it's almost half the weight of Hubble. And it lives at a place called Lagrange point 2, which might sound very mysterious if you don't know what that is. It's just a point very far away in space, whereas Hubble actually orbits the Earth. It's much, much closer. But again, I'll show you more about that in a second. So let's start with the beautiful gold mirrors of JWST. 6.5 meters from corner to corner. There's people here for scale, so you can see how large it really is. And they're gold because they really are coated in a very thin layer of gold, along with another element called beryllium. That's just because those elements reflect infrared light really well, so a normal mirror wouldn't reflect it as well. They're coating it in gold and beryllium specifically to make it extra good for infrared light. And it's made up of 18 hexagons, so these can all move individually to help focus things better if there's a problem. And when it was launched, you'll see that they all fold up amongst themselves, and it's frankly a miracle that this worked. And what's called the secondary mirror is this round gold one up here. This is 3/4 of a meter, which is bigger than any telescope you would see outside of a professional observatory, I think, on Earth. Like 3/4 of a meter is very big for a secondary mirror. So even that is very impressive. The previous infrared telescope that we had was called Spitzer, and its primary mirror was effectively the same size as that. So this was a huge step jump in the capabilities of infrared astronomy. When I say primary mirror and secondary mirror, I'm not sure if everyone knows what that means, so I just want to show you how light moves through the telescope, so how it bounces around all these mirrors when it comes from a distant object. So I'm hoping this will play. Okay, amazing. So this is light coming from some star or galaxy in the universe. It hits the primary hexagonal gold mirror. It gets focused by that mirror onto the secondary smaller one, and that then again focuses it into this sort of black bit in the middle, where it then bounces around a few more small mirrors, and then it goes off to whatever detector is being used at the time. So that's what's happening when light is passing through the telescope. It hits the primary mirror, gets focused onto the smaller secondary mirror, and then it sort of goes into where all the detectors are. And then there's a lot more tiny mirrors that just redirect it and stuff like that. Just to show you the size comparison of the mirrors, I don't know how tall this lady is, but she's a bit shorter than Hubble's mirror, and JWST's is a lot bigger. If you compare 2.4 and 6.5, that's 2 and a bit times bigger, but for astronomy, it's actually the area of the mirror that's most important. So over doubling the diameter, it gives you almost 6.5 times more area. So it's actually even more impressive than it sounds, in my opinion. And again, this is just to show you the whole telescopes to scale, with the mirrors particularly highlighted. So you can see the mirror is a lot bigger, and it's in a different place. It's very exposed because it's so big. We couldn't build a toilet roll to go around that. It was just too big. But it does leave it more exposed to little bits of space debris, so it's much more likely to get hit by things like that. So that's a consideration that makes this a lot harder than things like Hubble. And you can see it's got a quite different structure of the telescope. This has got one big sun shield, whereas Hubble has nothing as complicated as that. It's just in a tube. So speaking of the sun shield, I think after the mirror, it should be the second thing you notice, because it's the other massive thing on the telescope. It's almost the size of a tennis court, almost 70 feet long and 45 feet wide. And its primary goal is to keep the top bit of JWST as cold as possible. Because this is an infrared telescope, that's basically seeing heat. If the telescope itself is hot, it would just start seeing itself in its detectors. It would be like, there's loads of infrared light coming from here. It's very bright. So we have to keep it as cold as possible so that doesn't happen. And that helps us see very, very faint objects in the universe. So I think I have some good statistics. So the bottom of it will always be facing the sun to keep the instruments away from sunlight and the heat. And the top of it will be much colder because it's facing the vacuum of space. So it's 5 layers. They're incredibly thin and delicate. And they're a special material called Kapton, which I had never heard of before I started learning about the telescope. The sun-facing side, so the very bottom, reaches 383 Kelvin, which is over 100 degrees Celsius, which, that's too hot for anything infrared to be useful. Whereas the top side is just 36 Kelvin, which is minus 237 degrees Celsius. So that's effectively the temperature of empty space, which is just a little bit colder than it needs to be, so that's good. We're happy with colder than we need to be. The layers of the sun shield are separated to help the heat dissipate into space, so there will be nothing in between these. There's just the vacuum of space between it, which helps the heat dissipate, whereas if it was one solid sun shield, it would have much more conduction through the shield, and it would actually be a lot worse at protecting it from the heat. And this is what we call the passive cooling of the telescope. There is also one instrument, it's called MIRI, it's the mid-infrared instrument, and it needs to be even colder than space, so it actually has what we fancily call active cryocooling, but it's basically just an AC next to it to keep it nice and cold. And I think, I should have checked this before, but this 7 Kelvin, or minus 266 degrees Celsius, must make this one of the coldest places in the universe, because it's colder than the vacuum of space. Previously, we had a telescope called Planck, which was the coldest place in the universe for its time when it was operating. It was just like a fraction of a degree above absolute zero, if that means anything. And I think this must be pretty close to the record if it's not holding the record at the moment. So I've talked to you about a massive mirror, a massive sun shield, and it sounds great. Bigger is better for space telescopes. This sounds like a great plan, except for 2 things. It's really expensive, and to put something in space, you need a rocket, and we don't have any rockets this big. This is the major problem of, we want this big a mirror, but if it's bigger than the rocket, the fairing of the rocket, how are we going to get it into space? So this was precisely the problem. This is the launch of JWST. It was going to launch on an Ariane 5 rocket, which is a European rocket, and their fairing is about 5.5 meters. So no chance of fitting the mirror in, and definitely no chance of fitting the sun shield in. So instead, we had to come up with the most complicated thing I've ever seen, which was folding the telescope, the mirror itself and the sun shield up into a sort of cuboid shape, and putting it in the top of the rocket up here. And not only did we have to fold it up, which was very difficult, we then had to ask it to unfold by itself in space while traveling to where it's going to live, which was very difficult. And frankly, I went into work every day thinking, today's the day I'm going to hear that something has gone wrong. It had 344 single points of failure. So if any one of those things had not worked properly or had gone wrong, the telescope would not have operated as planned, and we would have had to do some major replanning of what we're going to use it for, because it simply would not be designed or fit for purpose that we designed it for. And just unfolding the primary mirror alone had almost 200 release mechanisms to get it go from squashed up cuboid to massive mirror. So this is just, I don't know, could we turn the lights down a little bit? Sorry. The animation I have is quite quite dark, it turns out. When we land things on the surface of the moon or Mars, we talk about a few minutes of terror because we can't control the probes as they go to land. This was like 2 months of terror. So it was a Mars mission or a moon mission ramped up to a crazy level. Thank you. So I hope you can see this animation. It will show you the telescope on the right and the rocket it went in on the left. You can see this is to scale at the I think this is to scale at the moment. Too big to fit in on the left. So instead, we had to fold up the sun shield, fold up the mirrors themselves and the secondary mirror. They fold up and put it in the telescope like that, in the rocket like that. That alone was difficult, to not rip the sun shield because it's so thin, and to make sure the mirrors are not broken in any way. Once it was in there, it looked like this, and it had to, first of all, survive a violent launch to space, which is normally the hardest part of the mission when you get it to go up. So this is there's lots of vibrations and everything happening there, which is always very scary. And this was, like I say, Christmas Day. Everyone's trying to cook their turkey, and I'm worrying about this. So eventually, the rocket opens up, the boosters have fallen off, it's going to release the telescope into space, and then you can see it all happen in reverse. So this is some of the primary mirror that's just knocking around on the side. And like I said, it was days and days of terror as we waited to hear and see whether it had worked properly. And I can tell you now it did. So this is how it unfolded. All autonomously in space, we couldn't control anything. But first of all, the sun shield came out. All the layers came out. They had to be tightened so they were as tight as they need to be. All the antennae and the solar panels had to fold out, and then we had to deal with the mirror itself and the secondary mirror. So the secondary mirror is folded up here. We call these the wings of the primary mirror. They're going to unfold in a second. There we go. And amazingly, it worked perfectly. We're all very happy. We could not believe it. But this is a modern-day miracle in astronomy, in my opinion, getting this to work. And the reason I mentioned how good it was because Hubble had some trouble when it launched back in the 90s. Its launch itself went very well, but when they started looking at the images it was taking, they realized there was a bit of a problem. They were all really blurry. And you launch a space telescope specifically because they're less blurry than ground-based telescopes. The ground-based telescopes have the atmosphere of the Earth to go through, and that makes things blurrier. We launched them into space to specifically avoid that problem. So when we saw them so blurry, it was very upsetting for everyone. I imagine. I wasn't there. And the issue was quite easy to pin down because both of the original cameras on Hubble saw exactly the same thing. So it wasn't a detector-based problem. It could only be the mirror. And it turns out it was shaped wrong. They're meant to be slightly curved so that they can focus the light onto their secondary mirror. But this one was too flat, just on the very edges, something that it caused a problem called spherical aberration, which was just that it wasn't focusing light in the right way. I can show you an example here. So this is what it should do. The light should bounce off the mirror at the bottom and be focused to a point here. And this is where the secondary mirror would be, and that would bounce it back down into the detectors down here. What was really happening was these bits on the edge were slightly too flat, and therefore they were reflecting the light in slightly the wrong direction, so it wasn't focusing properly on the secondary mirror. And that led to a blurry image rather than what we should have seen, which was a nice sharp one. Once they had realized the problem, they went back to the people that ground the mirror and said, how did this happen? And they found that the machine they used to verify the shape of the mirror was correct was slightly miscalibrated, and it was a 1.3 millimeter mistake that led to probably, if not hundreds of millions, billions of pounds. I said that the wrong round. If not billions, hundreds of millions of pounds to go and fix it. Because they were planning to send astronauts to Hubble to upgrade it regularly. Sorry, I keep standing too close to that. But they had to bring that forward because they needed the telescope to work quicker. Am I sounding too close? Okay. It sound okay to you? It sounds a bit fuzzy to me. Okay, so the solution they came up with was you can't change the mirror, but we can give Hubble glasses. So they literally just installed some lenses that the light then went through, which just helped focus it in the correct way. The astronauts, it was still 3 years later, I should say. There was still 3 years worth of images that astronomers had to deal with that were blurry, and they had to fix that in post, basically. But eventually, in '93, astronauts went up on the space shuttle, docked Hubble on the back of it, and installed the forced acronym of Corrective Optics Space Telescope Axial Replacement, or COSTAR, which they thought sounded great. I can show you COSTAR. This is the actual sort of module they strapped to Hubble, or the inside of Hubble. This astronaut is literally strapped to an arm here with their feet, and they are installing this onto Hubble, which is this big cylinder behind the astronaut, and this is the space shuttle. So they literally had to go up and give Hubble glasses to make it work. And the reason I bring this up is because JWST could not afford a problem like this. If this had happened to JWST, it would not have been a good telescope. We can't send astronauts to fix it. It is unreachable. It's just too far away. So before I rant about how far away JWST is, this is just a before and after of COSTAR. So before, you can see how blurry this is a star, so it should be a point-like object, really, a point or a small circle of light. And before they fixed it, you had all of this blurring. This like concentric circle artifacts were really, really bad, and it looked awful, frankly. And afterwards, you can see what an improvement it made. So we're very, very thankful for those astronauts. But the reason we can't fix JWST, or we couldn't have fixed JWST if we needed to, is that it's a lot further away. So Hubble orbits the Earth. This graphic says 570 kilometers up, but nowadays it's more like 550, 540. But it's orbiting the Earth. So when we had the space shuttle, it was relatively easy to access. And we did it 5 times, the last one in 2009. JWST over here is 1.5 million kilometers away. So I don't know how many times 570 goes into 1.5 million, but it's a lot further away. It's about 4 times further than the moon, which is the furthest we've ever sent people. So that just gives you hopefully a flavor of how difficult it would ever be to reach JWST. It's not possible in my lifetime, certainly, and probably not for hundreds of years that we would ever have the capability to go this far out. So when I said there was 344 single points of failure, that's why that was so scary, because we could not go and fix this. The only thing we could do for Webb is just slightly shake it, just ask it to rock back and forward, and just hope that if something was stuck, that was enough to get it to unfold properly. That's literally the extent of what we could do to it. So, yes, that's the difference. So it's about, what's this? 1% of the distance to the sun to JWST. So JWST lives here, this is the Earth and Moon, and the sun is 150 million kilometers away. And Hubble would be, somewhere right in here. So other than the size of the mirrors, the other difference between Hubble and JWST is the type of light they can see. So there is a whole spectrum of light, and it behaves in very different ways. So this end we have things like gamma rays, which are incredibly high energy, and they're really difficult to detect with telescopes, but we do have a couple. And then the spectrum of light goes through X-rays, ultraviolet, the visible light that we can see with our own eyes, and that's mostly what Hubble can see. And you can see this is a really thin strip of the electromagnetic spectrum. So the reason we send telescopes up that can see such different types of light is to see what we're missing, basically. And so JWST is mostly infrared. We also have microwave and radio, which are all types of light as well. So these ones are pretty easy to do from the ground. That's fine. These ones are incredibly difficult to do, but we normally do them in space. And this is the sort of range we're talking about today. And these different wavelengths, they show us objects differently. So infrared light, like I said, is like a heat map. And it's very good at getting through dust and gas that normally obscures things we might want to look at. So for example, when you're forming a new star, that forms from dust and gas in space, basically. So to actually see that process happening, you have to look through a lot of debris. And Hubble is okay at doing that, but not great. But infrared light is much more penetrative, and it can see through that dust a lot better. So I have an example that This was a weird day that I had where I said to my my loved ones, I'm just going to fill a room in our house with smoke. I hope that's okay. It's for science. And this is what that looked like in person. So you can see me just about, but it's hard to see any detail. The visible light is bouncing off all the smoke that I filled the room with, and it's quite hard to see details of my face and stuff. You can see different information in the infrared. So this is an infrared camera I used in the same smoky room, and you can see the outline of me a lot more. You still can't see like tons of detail in the face, but you can see where's the hottest and where's the coldest part of me. You can work out probably that I'm wearing a shirt and all this stuff from infrared light. You can even see this plant behind me, which is weirdly quite warm as well. So this is just to give you an idea of how the two telescopes would see the world differently. Hubble will mostly see what we would see with our own eyes, and JWST can often get through a bit deeper and see these new details that maybe Hubble will miss. And I don't recommend filling your house with smoke to do this. It made everything smell a bit weird, and it was really hard to get it all out. So this is just to put those telescopes on that spectrum. Hubble can see the visible light, a little bit of ultraviolet, and a tiny bit of infrared. And you can see that JWST range is a lot wider. It can see a lot more wavelengths of light. And these are much lower energy. So this is a lower energy side of things. This is the very energetic things. And I mean, I'm not good at remembering these numbers, but you can see that this is nanometers of the wavelength of light, if that means anything to you. JWST can see over 28,000, just about 28,000 in the range, and Hubble is less than 2,000. So that's the differences. What does that look like when you're taking pictures? This. So this is a Hubble picture of something we call the Pillars of Creation. When it was released, this was, I think, fair to say, one of the most beautiful space images that we'd taken. It's a nebula. It's part of the Eagle Nebula. And it's basically, like I said, just big towers of dust and gas floating in space, like unconceivably large. These are light years across each one of them. And you can, like, it's very beautiful, but you can see that there's a lot of dust and stuff in the way, and you can't really see too much detail. And then around here, you can see there's all this gas and dust, and we can't see behind it very much. When we go to JWST, which is this one, you can see we see through a lot of that gas and dust a lot better, and we can see many, many more stars, especially in the background, but also the stars that are forming in here. These red tips are brand new hot stars being born, many of them. And to give you an idea of the scale, our solar system would fit, easily in the tip of one of these branches. But this is really just an excuse for me to show you this picture, because when I saw it the first time, I was blown away. I love it so much. And I think it shows nicely the difference between these two telescopes and what the benefit of going to longer wavelengths and a bigger mirror is. So one of the difficulties is the longer the wavelength you're taking pictures at, the inherently worse resolution you have. If you have the same size mirror and you're looking at longer wavelengths with one, the image will be blurrier. So JWST has to be a lot bigger to even surpass Hubble's resolution, which was one of the challenges of this. I want to show you another picture. This is a galaxy cluster, this time rather than a nebula. And this was the first JWST picture ever released. There was a hilariously awkward press conference with Joe Biden and the head of NASA where they sat in a room and tried to reveal this and make it sound exciting. And somehow they made it sound boring. It was very disappointing. But the picture itself, I love. So these bright white areas are sort of thousands of galaxies that all look like they're merging together. This is a cluster of galaxies. And around them are galaxies that are more distant, and their light is being sort of warped and bent by the interference of this massive cluster in the way. I've nicknamed this guy the Dali galaxy because he looks like one of the clocks in the Salvador Dali painting. So it's not official, but I'm trying to start a thing. So I'm calling that the Dali galaxy. And these are all individual galaxies that are being bent and warped like this. And I love this picture for two reasons. One is the amazing stretching and warping of this, which is something we call gravitational lensing. But also, it gets me to show you this bright, spiky thing in the middle. So this is just a single star in the Milky Way. So this is a lot closer to us. This is in the galaxy we live in, this star, whereas these things are literally billions of light years away. So this is a lot smaller, but it's a lot closer. And I said earlier that stars should look sort of point-like and like a ball of light. And this one very clearly has sort of 6 spikes, which is a bit odd. These are called diffraction spikes, and I just want to spend a moment to talk about what they are, because you can use them to identify a JWST image. No other telescopes produce stars with these specific shapes of spikes. So why does JWST give its point-like things spikes? And the answer is not unexpected. We knew it was going to happen when we launched it, and it's to do with both the shape of the telescope, the fact that it's basically a hexagon, and the fact that we have the secondary mirror is here, and to hold that in place, you have to have struts to hold it up. It can't float there. We need it to be very stable, so we have to have 3 of these struts to hold it up. And what they do is they effectively block parts of the mirror from seeing light if it's coming head-on. And the effect of that is the wave physics behind it is too complicated. I don't understand it very well. But basically, the effect of having a stick that blocks some light is to get a perpendicular set of spikes. So if the star was in the middle, this strut here gives you 2 spikes either side. And then these struts do the same thing. They give you a perpendicular set of spikes. So if I can do this strut will give you these spikes, and this strut will give you these spikes. But the hexagonal shape of the mirror does the same thing. It reflects light in a slightly strange way, and each edge of the mirror gives you a perpendicular set of spikes. And when you add these things up, you get what we call the JWST diffraction pattern. So it's a combination of the struts and the shape of the mirror. We did design it as best we could to line up some of those spikes. So you can see that these cross ones here line up with these cross ones here, so we don't end up with 12 spikes. So we did our best, but you can always recognize a JWST image with these spikes. And just to compare that with other telescopes, this is what you would get with different combinations of mirrors and struts and the spikes you would cause. You can see that one strut gives you spikes in both directions, so having a single strut or a double strut is actually basically the same. But the important characters here are, this is what Hubble's mirror looks like. It's circular with a cross of struts, so you always have 4 spikes on Hubble images, in stars in Hubble images. And this is what the Euclid Space Telescope looks like. It has 3 struts, giving you 6 rather than 8 from JWST. And just to compare you there, this is a Hubble star, this is a JWST star. Some people that I know are always impressed that I can spot a JWST image straight away. They say, oh, look at this picture. And I'm like, oh, JWST took that. They're like, how did he know that? That's amazing. It's the spikes. The spikes give it away. The spikes give it away instantly. No other telescope makes the stars look like that. It's very easy. More telescopes give you a cross like this, so it's a bit harder to pick up our Hubble one. But feel free to remember that and look smart if anyone ever says, check out this picture. Okay, I don't want to dwell too much on this, but I just wanted to show you, or at least name the instruments that that JWST has on board. So it has 2 cameras that image near-infrared light NIRCam, the near-infrared camera, and the mid-infrared instrument mirror. You can see we're really bad at acronyms. We made these work. This is also a camera and also a spectrograph, and then there's a near-infrared spectrograph called NIRSpec, and a more complicated name that is basically another spectrograph. And what they do is they break down light into its component wavelengths. So rather than just taking one picture, they sort of break that light up like a prism would. You know, the cover of the... Who? I've never heard of Pink Floyd. The cover of The Dark Side of the Moon is a prism. JWST is doing the same thing, but rather than doing visible light into a rainbow, it's infrared light into an infrared rainbow. So spectrographs break up light, and that's very useful for a lot of things that I'll touch on in a minute. And also, I have to mention you'll notice I said 4, and then I've listed 5 things. It's because this is just the guidance sensor, so it's just how JWST steers and knows what it's looking at. But it does have a camera, and it's on the next graphic I want to show you, so I thought if I didn't name it here, someone might be upset. So this is just the last calibration images from each detector when we finally said it's ready to use for science. They released a little snapshot from each one. And you can see the Fine Guidance Center has a small camera on board so that it knows what it's looking at. It has to look out at the stars and it finds stars that it recognizes, and that's how it sort of compares a map, so it knows where it's looking. And these are just quick examples of the shapes of the detectors of everything else, but this isn't too important, so I just wanted to touch on it very quickly. This is to show you the difference between looking in the near-infrared and the mid-infrared, when it might sound like those are really the same thing. So on the left here, we have an object called the Southern Ring Nebula. There's a star in the center, and then it's blown off shells of gas and dust and all sorts of space gunk. And first of all, I think it looks amazing. You can see a lot of structure in this gas that it's just not possible to see without JWST. And this was one of the very first images released by the telescope. And on the right is exactly the same object, but this is in mid-infrared, whereas this is in near-infrared. And the colors are different, sure, that's one difference. But you can see, like if you look at this streaky thing in the background, you can see it in a lot more detail in the mid-infrared, because it's even better at looking through all the dust. And if you look in the center, you can see that that star is actually two stars. This is something we didn't know before JWST. At the center of this object, there is at least two stars interacting, causing this sort of bubble shape to be blown off from the object. So they look different. You can see what I mentioned earlier. The longer wavelength is slightly lower resolution. This is a slightly blurrier image, and that's just because it's a longer wavelength of light. And the other thing you can notice is that stars are generally a lot less bright in longer wavelengths. So in mirror images, everything looks a lot fainter because stars just give off less light in this wavelength. This is another comparison to show you that difference. This is what we saw earlier. So there's our Dali galaxy. This is near-infrared on the right and mid-infrared on the left. So you can see everything gets a lot fainter, but around bright objects, this is really helpful because if you have something faint next to something bright, it's hard to see if you have these big spikes over it. So this is useful for seeing faint objects near bright things and for peering deeper through gas like we just saw. And this is just my favorite picture from JWST. I think, I don't have anything clever to say about it. It's just like, oh, good stuff. So this is called the Carina Nebula. It's part of a much larger structure, but it's again just dust and gas that has happened to be gravitationally interacting. It's bound together in this sort of like orange wall. This is the gas and the dust. And the detail that we can see here is just unbelievable compared to anything we've had before. You can see through a lot of the dust and gas, so you can see the details, and then you can see stars through it, then often forming in this cloud too. And you can see, if you look carefully, you can see sort of wispy structures coming off the top of this wall, almost. And this is literally where the radiation from new stars is heating up that dust and gas, and it's literally blowing off, it's sort of almost boiling off dust and gas and making these nice wispy structures. And I mean, just the background of it is, oh, it's 10 out of 10. I love this one so much. So nothing smart to say, just I wanted you to all see this in case, if you don't take anything away, just take away this picture. And then I should also compare Hubble and JWST side by side. So this is an object called the Crab Nebula, or the Crab Pulsar. This used to be a star, and a few hundred years ago it exploded. This is what we call a supernova remnant. So this is the Hubble image, which again, we all thought was amazing when it was taken. But recently, JWST released this one of the same object. And I just think it's another level. You can see, it looks almost much more 3D. You can see through the gas and the structures look more defined. You can see more structure in different places. And what's interesting is that most space objects are very large, so we don't see them change on human timescales. But this one is just about small enough that between the two, we could see it expand. So this was a few years between these two images. And I don't think I've put them to the right scale here. But if you compare them properly, you can see it sort of keep getting bigger and change over the last few years, which is a rare thing for astronomy. But as well as beautiful things like I've just shown you, Webb sees sort of blobs like this. And this again was very exciting when we saw it, because this is one of the most distant galaxies we've ever seen. And the more distant things are, the more blurry and small they look. So it looks visually maybe less impressive. But this is a galaxy that had formed by the time the universe was just 390 million years old. And maybe the word just there is a bit, a bit misplaced. But the universe is now about 13.8 billion years old. So comparatively, this is very young. I know this is a long time, but comparatively, this is very young. And we didn't really expect to see many galaxies around that early. And the fact that JWST saw this one, and we can confirm how old it is, it was a very special thing when we saw it. And this is the first time we've been able to see that far back in history. And because we're bad at naming things, we finally got one right here, and the discoverer named it after his daughter, who said that she wanted a galaxy named after her. So this is now officially Maisie's galaxy, named after a kid somewhere in America. But again, it doesn't look impressive, I think, but it was very exciting when it happened. And this is just one final deep field shot from JWST I want to show you. Have many people heard of the Hubble Ultra Deep Field? It's a region of, it's a picture that Hubble took where it literally pointed at the darkest patch of space it could find, and it pointed there for about, I think it was about 11 days. And they expected to see not very much, but when the picture came back, there was thousands and thousands and thousands of galaxies, just to show that, or showing that even in the darkest spaces, if you can see deep enough, you can see a lot of galaxies. Each one of these contains billions of stars. So it was mind-blowing when it happened. The mind-blowing thing about JWST is it effectively completely reproduced that 11-day image in about 20 hours. So it saw about the same number of galaxies, but it did it in less than a tenth of the time. And this is the most recent JWST deep field I've seen, but once we get ones that are comparable in length to Hubble, it's going to be even better, and I'm very excited for when that happens. So JWST is good at looking for galaxies and nebulae, but it's also good at looking for planets. And it's much harder to image distant planets, but it has had a go. And it's also looked for things called biosignatures. So these are tracers on other planets that might suggest there's life there. We can't see those planets well enough to say, oh, there's trees on that planet or there's cars on that planet. But we can maybe see signatures that would only be there if life was there. So there are some gases and some molecules on Earth that we don't know anything else that produces them other than respiring or living things breathing in and out and breaking down certain compounds. And we call these biosignatures, and that's what we're looking for with JWST. We haven't found any yet, but we've had a good go. So this is, I mentioned earlier, a spectrum. It's where you break down light into its component wavelengths. But the important thing here is if you see a dip in a spectrum, it means you can identify an element or a molecule. So the spectrum of Earth, there's a lot of carbon dioxide, there's a lot of ozone, and a lot of water. That's what these dips tell us. And we're basically looking for planets that have similar shapes in their spectrum. We found this. So this is an exoplanet with a sort of telephone number name. And it had this interesting molecule called dimethyl sulfide, which I had to practice saying a few times before tonight. And it is potentially a biosignature if we can confirm this detection. You can see the dip under that name is less convincing than other dips, or other bumps in this case. But just know that JWST is looking for these things, and hopefully one day we'll see something at least exciting, if not a picture. We won't see a picture of a tree, but we might see something exciting. But I want to show you some nice pictures of planets. I can't leave it with these lines. So JWST has imaged planets in our own solar system. So this is Neptune, the most distant planet in the solar system. And I hope a few of you are going, I didn't know Neptune had rings. This is real rings around Neptune that exist. And these are moons of Neptune, including this really bright guy up here. So I don't know if you've seen pictures of Neptune before, but this is a pretty good one. Similarly, we can have Jupiter. Again, it's got rings, and we can see an amazing amount of structure in the sort of bands of Jupiter that we have here. This is normally the Great Red Spot. It's colored white here. I don't know why. And these are actually aurorae on the north and south pole of Jupiter. So I hope some of you saw the Northern Lights recently. Those things happen on other planets too, and we can see them here with JWST on Jupiter. This is Saturn, and this is impressive because this is just a 4-minute exposure. So normally to get pictures this impressive, you would have to look at a planet for a long time. But JWST, this is one wavelength of light, and it's just 4 minutes. You can see the gaps in the rings really nicely. You can see some of the moons. And I think it's pretty good. The reason the planet itself is so dark is because Saturn has a lot of methane in its atmosphere, and methane absorbs this one wavelength of light really well, so it looks very dark in that wavelength. But the rings don't behave in that way, so they look nice and bright. And finally, everyone's favorite planet, Uranus also has a lot of rings around it. Apparently there's 13. I can't count 13 there, but I've been assured there's 13. But again, getting pictures like this of Uranus from a space telescope in just a couple of hours is incredible. And I really like this image of Uranus. And it's not looking for galaxies, but JWST can't help but image galaxies in the background. It just happens. That's how good it is at collecting light. And just to compare, this is Uranus from Hubble. It's not bad. You can see at least one ring, but come on. That's just a zoom in. And then I have a family photo of the solar system from JWST. So this is Mars from JWST. These two are really hard to image because for the telescope, they actually move very fast. So to track it long enough to get a good picture is really difficult. And these are about the limit of fast objects that JWST can track. This is a different picture of Uranus, but also from JWST. And I just like this family photo. It can't see any of the inner planets like Mars, Venus, or Mercury. Thank you for the help. Because they're too close to the sun, they would just be too hot and bright. They would just burn out its detectors. So it can only see these more distant and faint planets. Right, do I have a little bit of time to mention one more? Yep. Just a little? Yep. Yeah? Great. I wanted to talk quickly about the Euclid Space Telescope, because it looks more like Hubble, but is very different in a few ways. It launched just last year. It is visible and infrared. It cost about $1.5 billion, but we're hoping to image over 2 billion galaxies with it. So, per galaxy, this is a bargain. I'm convinced on this one. Its mirror is 1.2 meters. It's going to last for about 6 years, and it's at the same point as JWST at Lagrange point 2. So it's also 1.5 million kilometers away. And it, as I said, its goal is to make the largest 3D map of the universe ever and teach us things about the mysterious dark energy and dark matter. And please ask about those if you don't know what they are. I just don't have time to go into it now. But it's an exciting mission that we're a part of in Portsmouth. It launched on a SpaceX rocket. The war in Ukraine meant that the planned Soyuz rocket was scuppered, so we had to very quickly find a replacement rocket to launch it, which was more complicated than it might sound. And it's currently working pretty well in space. It has 2 detectors compared to JWST's 4. So it has a visible light detector and a near infrared. So it sort of spans a similar things that Hubble and JWST can do. But the difference is that Euclid isn't going to image specific individual objects. It's what we call a survey telescope. So it's going to image the sky systematically in order to make this massive map of the universe. So over the next 6 years, these are the patches that it's going to survey. It's going to do about a third of the sky, avoiding the Milky Way galactic plane, because it's really hard to see faint things through all of the stars in our own galaxy. But it won't be regularly releasing beautiful things like JWST does, because it's just trying to make a massive map and collect as much information as possible. This is a recent image that it did take just to show off that it is working. So everything I've just said is true, but it did take a couple just to show off. This is called the Horsehead Nebula. And the impressive thing about this is that this is a single field of view for Euclid. So normally space pictures are made up of many frames because they can only see a very small patch of sky at once. So they would normally sort of tile those together and make one image. For Euclid, its field of view is massive compared to the other telescopes. And this is one shot. This is this is less than one shot. I've cropped this in, but it's another galaxy cluster similar to what we saw with JWST. So these are thousands of galaxies here in the bright white, and these are just galaxies in the background for days. There are tens of thousands in the image. And I just threw this slide in today, I've just remembered, because today we released these pictures from Euclid. You will probably be one of the first talk audiences to be shown these images because they released like a few hours ago. So I was very excited and threw them on a slide, but I didn't know where to put it. So I just wanted to show you This is another nebula, and this is a spiral galaxy, just to show off Euclid and how good it looks. So again, please come and ask me if you want later. But this is the crux of it. This is what Euclid can see in one go. It images all of these things in one go. So it's bigger than the full moon. These squares here are what JWST can see in one go. And these are two different Hubble detectors, what they can image in one go. So I really want you to take away, if nothing else, if anyone says to you, Euclid Space Telescope, you say, oh, it's got a massive field of view. That's the important thing, because that's how it's going to image the sky so quickly. To do a third of the night sky in 6 years might sound slow, but that's actually very rapid, and it does that with this massive field of view. So this is its visible detector, and this is its near-infrared. They're slightly different, but pretty similar, and the differences are still very massive. This is the Pegasus cluster zoomed out. I just showed you this is the galaxy cluster that Euclid imaged. This is one field of view for Euclid, as I said. If I flip to this slide, each one of these squares is what Hubble has imaged of the cluster. So in the last 34 years, Hubble hasn't even imaged this whole single field of view that Euclid took in, this is an hour for Euclid, and this is days of Hubble time to try and get as much as it can, and it's just done these black squares. So that is the key difference between Hubble and Euclid, is the size. This is a single field of view. This is a single field of view of the same object. This is to scale and of the same bit in the middle. I just have a few of these now to end with. This is a single Euclid field of view. This is 9 Hubble fields of view of the Horsehead Nebula. So it looks beautiful, but this took orders of magnitude longer to image than the Euclid one did. And this is a JWST field of view. So these are designed to be zooming into objects and taking really detailed, intricate photos, whereas Euclid is designed to make massive maps and take these really wide fields of view. Should I wrap up? I have like 2 slides left. This is like my last slide, just to say what's next, because these things are amazing, but science never stops. We want to keep going. So these are just names of some future telescopes. This is the next big one to launch that you might hear about is the Nancy Grace Roman Space Telescope. It's sort of like Euclid, it's got a massive field of view, and it's going to be studying dark energy. Then we have one specifically looking for exoplanets, so these are planets outside our solar system. It's called the Habitable Worlds Observatory, and it will, again, launch probably in the next decade. And then this monstrosity up here is an idea, it's not confirmed, it's just called LUVOIR, which, if I can remember, is the Large Ultraviolet Optical and Infrared Surveyor. So this is just JWST on steroids that maybe in 20 or 30 years we might see happen. And then the ones in blue are ground-based telescopes. So these are massive instruments that will be built on the ground. This is the 30-meter telescope. Anyone want to guess how big its mirror is going to be? It's pretty good, right? This might happen in the next few years. And then the final one I put on the list is called the Square Kilometer Array. This is a set of radio telescopes. So they're big radio dishes that you might have seen before. But there'll be hundreds of them in South Africa and Australia. And if you add up all of their total collecting area, you get a square kilometer. So it's very ambitious, but it will be very good for radio astronomy. And this was just to compare the Euclid field of view with this future Nancy Grace Roman. So in a few years, Euclid will finally have competition for size, but not yet. These are the old JWST and Hubble ones as well. And I will finally stop there. Sorry for going slightly over, but please feel free to ask any questions. Thank you very much for listening.